Hello, so today I'm up to the end of chapter 4. Chapter 4 is about creation and this subsection is entitled fine-tuning. We've already dealt with creation in terms of biological knowledge. One of the interesting things we're now getting to is this huge issue in physics and philosophy of the fine-tuning of the laws of physics, or the constants of nature, or the parameters of nature, however people like to put it. If there's one issue that it doesn't matter what kind of physics you're interested in, that physicists in general seem to converge upon. So in my experience, it doesn't matter who the physicist is, everyone seems to have an opinion on this. And the issue is whether or not it's a problem in science as to the degree to which the laws of physics appear to be bio-friendly. So this is all about why the laws of physics have the form that they do. It seems unusual when we look at the details of what the kinds of laws of physics are that we have and the constants of nature that appear in those physical laws. It appears that values all sit on a knife edge, that if you were to change any of them ever so slightly, then the conditions, which are at the moment in this universe favourable for life, would quickly turn the universe into one that isn't favourable for life. So I'm going to have a look at some issues surrounding that. There's been a lot of books written on this. So when I was in high school, I was interested in science, I was interested in physics, I was interested in astronomy. And it was towards the end of high school that I picked up The Mind of God by Paul Davies. And this is the book for which he won the Templeton Prize, which is a very well remunerated prize. I think it's in the millions of dollars. And it was an excellent book. It was basically an overview of physics as it stood at the time, at the late 90s. And a lot of philosophy. It was really a summary of important issues in metaphysics and ontology, but really it also concentrated on this very question about whether or not the laws of physics appear to have been a put-up job. That's the way that Paul Davies often put the issue. It seems like it's a put-up job. It seems as if the laws of physics have been especially bio-friendly. Now, Paul Davies, like many physicists on this topic, don't come down on one side or the other as to what the underlying explanation is. Many present the options and allow the listener to decide for themselves. There's an interesting phenomena here socially as well when we get into talking about this fine-tuning of the laws of physics. But mainly people who are interested in the issue of religion and arguments for and against religion. There's some people who want to reject the issue outright. There's a school of thought who says it's just a coincidence. Why can't you accept it's a coincidence? The laws of physics are the way they are, and we just happen to have appeared in a universe where the laws of physics have the form they do. Now, of course, this isn't an explanation. A coincidence isn't an explanation. I might mention a few books here. I've mentioned Paul Davies' The Mind of God. Paul Davies has many books on this topic. One of the more recent ones that he wrote was called The Goldilocks Enigma, and that's another fantastic book specifically about why it is that not only does Earth occupy the physical place that it does around the sun, that's probably a coincidence, but also all of the other kind of coincidences that appear to be out there in terms of the physical constants. So if I could just give an example that's often cited when we speak about the universal gravitational constant G. The universal gravitational constant G is one of the things that gives strength to gravity in our universe. Whether you're using Newton's law of gravity or Einstein's general relativity, it doesn't matter. This universal gravitational constant appears in the equations. It has a certain value. It determines the strength of gravity within our universe. If that constant was even fractionally greater, and we're talking fractions of a percent, then what would happen is that stars would collapse into black holes, and we'd have a featureless universe. If we don't have stars, then we're not going to have complex elements. And so we're not going to have planets, and we're certainly not going to have life. We'd have a universe devoid of chemistry. On the other hand, if the gravitational constant was much weaker, stars might not form at all. As the hydrogen began to collapse, what would happen is that it would heat up, and then it would start to expand again under thermodynamical rules. So the value of the gravitational constant seems to be finely tuned. Another book on this topic is by a couple of Australians. It was published last year, I believe, and it's called A Fortunate Universe. It's by Luke Barnes and Geraint Lewis. And Luke Barnes is at the University of Western Sydney. Geraint Lewis is at the University of Sydney. And they wrote this fantastic book as well. And it traverses all of these issues about fine tuning. And the way that Luke likes to put things is to consider if you had a safe, and the safe had a whole number of dials that you need to twiddle in order to gain access to the safe. We don't really know what all the constants in nature are. I've seen a number like 26. So let's go with 26. If there were 26 dials on this safe and someone broke into the safe, what would be the explanation of how they got in? One possibility is that it could be pure coincidence. They've fiddled with the dials and they've managed to pick the correct number on every single one of those 26 dials. That would be a terribly bad explanation. That is not what the police would assume if someone had broken into the safe. They'd assume they already had knowledge of what the numbers on the dials should be. And so that seems to be the situation in which we find ourselves. Of course, one objection to the safe analogy might be, for example, that there could be many different combinations that give you access to the safe. We don't know what all the different combinations of constants of nature there are in order to gain a bio-friendly universe. Some of these constants of nature, by the way, include things not only like the gravitational constant, but other things like the mass of an electron, or the mass of a quark, or the charge on an electron. This thing called the fine structure constant, which determines the strength of the electromagnetic force. So how closely, for example, electrons orbit nuclei around atoms. These things determine the formation of molecules. These things determine whether or not DNA can form self-replicating molecules and ultimately life. So it seems like we have a problem. Now, not everyone thinks that we have a problem. The late Victor Stenger, who was a particle physicist, wrote a bunch of books on this, bunch of papers, gave a bunch of talks. Just prior to when he died in 2014, I think, I actually wrote to Victor Stenger because I was writing a project myself. I was finishing my master's in astronomy, and so I wrote to Victor Stenger because he was about to publish a book. He hadn't published it yet, and so I really needed the information for the project that I had. His book was called The Fallacy of Fine Tuning, and it was coming out at the time, so I thought I need to get a hold of this book. I was very grateful he actually sent me a copy of the book before it was published. So with Stenger, the hint is in the title of the book, The Fallacy of Fine Tuning. And he doesn't buy it. He doesn't buy this idea that there's any special mystery to be solved here. I disagree with him, but he basically thinks that there's just a lack of knowledge that we've got here. One example he uses, which isn't one that these days is brought up very often, but just as a related issue, I suppose. The great Fred Hoyle, who was the astrophysicist to whom we owe much credit for explaining the origin of all the elements. Stellar nucleosynthesis is what he explained. So how it is that the elements are forged inside of the cores of stars. He had a problem. One of the problems was in trying to explain early on how different nuclear reactions happen, different fusion reactions happen inside of stars. We had great difficulty in trying to figure out how carbon was formed. The way in which carbon is formed is through a process called the triple alpha process. So what you need in order to create a carbon nucleus is 3 alpha particles, 3 helium nuclei. A helium nucleus has 2 protons, whereas a carbon nucleus has got 6 protons. So you need 3 of them to crash into each other in order to form this carbon nucleus. The problem is that if you take 3 helium nuclei, each of those helium nuclei having 2 protons has got a charge of 2+. And positive charges repel one another. And so when you try and get 3 of them together, they don't want to go together. So you need exceedingly high energies. It's an exceedingly unlikely event to occur, to get 3 objects, all of which have positive charges, to combine and to stick together. That's what you need for fusion. So Hoyle had a problem here, thinking that that was just too unlikely. He'd done the calculations that I don't understand. But as it turns out, the mathematics shows that this particular event is exceedingly unlikely to occur. So they had a workaround, and they figured out that if you take 2 helium nuclei, you can form a nucleus of beryllium. And then if the beryllium collides with another helium nucleus, then you can get carbon. But they found that even this was too unlikely because the beryllium nucleus lasts for a tiny, tiny, tiny fraction of a second, too short in order to form the carbon that was required. Unless, and Hoyle predicted this, unless the carbon nucleus thus formed was of high energy, had a particularly high energy. It's called a resonant state. So he predicted that this resonant state would exist, but this resonant state itself was exceedingly unlikely. It happened at extremely precise. It happens at a particular energy. This appeared to be suspiciously finely tuned. If the carbon nucleus formed from the collision of these two helium together to form the beryllium, and then having a third helium nucleus combined with the beryllium, if the carbon nucleus thus formed didn't have precisely this energy, then you wouldn't end up with carbon at all. And so this seemed to be a mystery. And so this is called the Hoyle resonance. He kind of solved the problem in one respect, namely this is how carbon is formed, but in the other raised a problem. Namely, why should this energy be so precise? Why should it be at that particular level? Why couldn't you form carbon at any level? And I bought this for a while. I read this both in The Mind of God by Paul Davies and then later on in The Goldilocks Enigma. But in doing research for the project I undertook, I then found a paper by another astrophysicist called Mario Livio. And Mario Livio calculated that the Hoyle resonance wasn't so precise after all. That if you try to create carbon at energy slightly different, then you will indeed get carbon. In fact, you will get the same amount of carbon in our universe if the Hoyle resonance was ever so slightly different to what it actually is in our universe. So what Mario Livio found was that you could fiddle with this very precise value for the Hoyle resonance by a small amount and still get the same amount of carbon being produced in our universe inside the core of stars as what you actually do see in our universe. So if you change the Hoyle resonance, you'd still get carbon. Indeed, you can change the value of the resonant state of this carbon nucleus by quite a bit and still end up with sufficient carbon in the universe for life to appear. And so this is one of the arguments that Stenger points to and says that, well, maybe all of the fine-tuning type problems will turn out to be like this, that if you vary the constants one after another, you will end up nonetheless producing bio-friendly laws. So he's not particularly impressed by it. Of course, my purpose here isn't to go through all the surrounding literature on the fine-tuning argument. I'll provide a link to the paper that I wrote. In fact, I might even read that paper at some point, which does provide an overview of the broad issues. But I'd encourage people to get A Fortunate Universe is a great book about this fine-tuning problem. And it's a great book because the two physicists that have written it have come from quite different places. They both agree it's a problem, but on the one hand, Grant Lewis says, well, possibly the multiverse could explain this. Now, when I say multiverse, I should probably say megaverse, although there's this nomenclature problem. There's this difficulty with terminology. Multiverse, of course, to me, to David Deutsch, to many other people, means the quantum multiverse. And in the quantum multiverse, all the universes obey precisely the same laws of physics. Indeed, it's the laws of physics that tell us that this quantum multiverse must exist. On the other hand, there is a whole bunch of people who use the word multiverse in a completely different sense, to talk about an ensemble of universes, each of which obeys different physical laws. So it would be like a multiverse of multiverses. And so this is why sometimes I just refer to it as the Megaverse. The Megaverse is scientific in some senses, metaphysical in other senses. There's a sense in which it really is scientific now. I've come to convince myself, and through some of the work that Luke Barnes has been doing recently on trying to simulate some of these other universes. So we don't have access to these other universes, we don't think, the physical access, which kind of relegates these theories to something like string theory. So it's difficult to understand how we can test this experimentally. But there's a weak sense in which we can test them experimentally, I think, by simulating these universes inside of a virtual reality. At the moment, those simulations are a very low resolution, so whether or not the calculations that are done inside of these supercomputers, modeling other physical laws or sets of physical laws, how robust those calculations are, time will tell, and as time goes on and we get better and better supercomputers, then maybe quantum computers will be able to help with this, by the way. So when I say we don't have access to these universes, one other postscript before I get into reading the beginning of infinity, the relevant part here, and that postscript is, some years ago, a team of physicists at primarily the University of New South Wales, led by John Webb and Michael Murphy, did some excellent, interesting work on looking at the change, the possible change in what's called the fine structure constant that I mentioned earlier. This fine structure constant appears in our laws of physics. It is the thing that sets the strength of the electromagnetic force. So in the same way that we have a constant, G, that sets the value of gravity, there's another constant that sets how strong the electromagnetic force is in our universe. And that determines things like the size of atoms and therefore bond strength between molecules, and therefore whether or not complex molecules can exist and whether or not life can exist. What this experiment involved was taking some of the most powerful telescopes on Earth, some of the telescopes that are on the top of those big volcanoes in Hawaii, and using those reflecting telescopes to peer into the very distant parts of the universe where light from quasars was coming. And that light from quasars, in its transit between the quasar and us, can in some cases pass through other galaxies. And as it passes through other galaxies, some of that light is absorbed. And one of the remarkable things in astronomy, one of the remarkable things that allow us to know about what's out there, are these things called absorption spectra. And in the absorption spectra, when we look at the light coming from the quasars, we see that some of the light has been absorbed. And that light is characteristic, the light that's been absorbed is characteristic of the kinds of materials that are inside the galaxy. Long story short, when we look at the lines, the absorption lines, I'll put a picture up here somewhere, of the light coming from the quasars, the distance between the lines is well known in the laboratory. And it's well known in astrophysics as to what the distance between these particular lines is. Now, what lines they're looking at, it depends. It could be absorption lines from hydrogen, but in this case, I think they used in part magnesium. What they found, and this was a remarkable finding at the time, was that the lines were ever so slightly different in terms of their distance in the distant quasar, in the distant galaxy as compared to what they are here in the laboratory. This has got nothing to do with redshift. It's a completely separate issue to that. Okay, all the lines were redshifted because the galaxies are moving away and the quasars moving away. So very, very complicated. They're looking at the distance between the lines because everything should get shifted by the same amount, and they found a difference. And so this was very exciting. And I'm saying this because if the constants of nature are somewhere different, are different in some distant part of the universe, then we have to start questioning what we mean by universe. What we mean by universe, because a universe is something that obeys a set of physical laws, at least in part. That's one way we could define it. Everything in the universe obeys the same set of physical laws. So therefore, it has the same constants of nature. So if we were to find a region of space out there where the constants of nature were different, if we could see it via some technique by using a telescope such as Michael Murphy and the rest did, their team did, then we'd kind of be seeing another universe. We'd be seeing a universe that obeys a different set of physical laws. So this was exciting at the time because to me it sort of implied perhaps that as you get further and further away, kind of going back in time as well, but as you're going further and further away, maybe you're seeing into an ever so slightly different universe. And maybe if you could see even further, you'd see a wildly different universe and so on. Okay, kind of a bizarre idea. As it was, sadness struck a few years ago when they found out that all of the results that they published were infected by the same systematic error. I'll provide a link to the papers, and if you're interested in looking at that, it's something that I found really fascinating, not only in terms of the physics. I think it was a really important physics technique that they figured out, but not only that, this is a wonderful example of how science is self-correcting, because immediately Michael and his team published all their results saying, we have got this excellent technique, but the things that we said about the fine structure constant changing aren't actually true. So they haven't found the fine structure constant changing, but it's still, nonetheless, it could be a technique for literally seeing another universe, possibly. So let's just preface what we're about to hear from the beginning of infinity with the possibilities of what's going on with this fine tuning. So it seems like electrons have just the right charge in order for complex molecules to exist. It seems like the value of gravity is just right for stars to form and planets to form. It seems like all the other constants of nature that we could enumerate have just the right values, such that if they were any different, then we wouldn't have life in the universe at all. We'd have some boring universe that was nothing but a black hole, or a boring universe that was nothing but gas. The two options before us appear to be, and are most commonly said to be, either a designer has created this universe such that it's bio-friendly. Paul Davies kind of puts it as, it appears like the universe has a purpose. He's not saying there's necessarily a designer, but there's some kind of purpose behind it all. There's some reason behind it all. And so if there's a reason, then it's no wonder that the universe is bio-friendly, because maybe we are the reason. We are the universe trying to look at itself or something like that, okay? But again, we're starting to get into metaphysics there. On the other hand, people who reject that and don't like that will go to or jump to this idea of the Megaverse, or the cosmological multiverse, where every single possible set of physical laws that we can imagine that is possible, perhaps beyond what we can imagine, but every set of physical laws that is possible, I think it's a class actually, in other words, it's an uncountable number, and there's no way to even begin counting this number. It's an infinite class of universes, an infinite class of physical laws, that if all of them exist, then we are just one of the infinite number that exists. And so therefore the mystery is solved, because all the universes are out there, most of them aren't filled with life. And so we find ourselves in one where it's possible to have life. So the wonderful thing now about David Deutsch's approach to this, of course, every issue that he raises, he's going to put his own personal spin on it, and this is no exception. And so I'm very excited to read the next part of Creation, Chapter 4, Fine-Tuning. So let's just get into it. He writes, under the subtitle Fine-Tuning, the physicist Brandon Carter calculated in 1974 that if the strength of the interaction between charged particles were a few percent smaller, no planets would ever have formed, and the only condensed objects in the universe would be stars. And if it were a few percent greater, then no stars would ever explode, and so no elements other than hydrogen and helium would exist outside of them. In either case, there would be no complex chemistry, and presumably no life. Another example. If the initial expansion rate of the universe at the Big Bang had been slightly higher, no stars would have formed, and there would be nothing in the universe but hydrogen, at an extremely low and ever-decreasing density. If it had been slightly lower, the universe would have recollapsed soon after the Big Bang. Similar results have since been obtained for other constants of physics that are not determined by any known theory. For most, if not all of them, it seems that if they had been slightly different, there would have been no possibility for life to exist. This is a remarkable fact, which has even been cited as evidence that those constants were intentionally fine-tuned, i.e. designed by a supernatural being. This is a new version of creationism, and of the design argument, now based on the appearance of design in the laws of physics. Ironically, given the history of the controversy, the new argument is that the laws of physics must have been designed to create a biosphere by Darwinian evolution. It even persuaded the philosopher Antony Flew, formerly an enthusiastic advocate of atheism, of the existence of a supernatural designer, but it should not have. As I shall explain in a moment, it is not even clear that this fine-tuning constitutes an appearance of design in Paleys' sense. But even if it does, that does not alter the fact that invoking the supernatural makes for a bad explanation. And in any case, arguing for supernatural explanations on the grounds that a current scientific explanation is flawed or lacking is just a mistake. As we carved in stone in Chapter 3, problems are inevitable. There are always unsolved problems, but they get solved. Science continues to make progress, even or especially after making great discoveries, because the discoveries themselves reveal further problems. This is me talking now. I'm just prefacing the next point with, this has been, according to my Kindle, highlighted 80 times around the world. So I'll just read this to you. The next sentence says, therefore, the existence of an unsolved problem in physics is no more evidence for a supernatural explanation than the existence of an unsolved crime is evidence that a ghost committed it. A simple objection to the idea that fine-tuning requires an explanation at all is that we have no good explanation implying that planets are essential to the formation of life, or that chemistry is. The physicist Robert Ford wrote a superb science fiction story, Dragon's Egg, based on the premise that information could be stored and processed, and life and intelligence could evolve through the interactions between neutrons on the surface of a neutron star, a star that has collapsed gravitationally to a diameter of only a few kilometres, making it so dense that most of its matter has been transmuted into neutrons. It is not known whether this hypothetical neutron analogue of chemistry exists, nor whether it could exist if the laws of physics were slightly different. Nor do we have any idea what other sorts of environment permitting the emergence of life would exist under those variant laws. The idea that similar laws of physics can be expected to give rise to similar environments is undermined by the very existence of fine-tuning. Nevertheless, regardless of whether the fine-tuning constitutes an appearance of design or not, it does constitute a legitimate and significant scientific problem for the following reason. If the truth is that the constants of nature are not fine-tuned to produce life after all, because most slight variations in them do still permit life and intelligence to evolve somehow, though in dramatically different types of environment, then this would be an unexplained regularity in nature, and hence a problem for science to address. So that's really interesting. So if changing the laws of physics higgledy-piggledy, changing the conservation of momentum law, changing the law of gravitation, changing constants of nature, if changing these still permits life to arise, then that's a regularity in nature. That's really unusual. It's like, why do all these variations still cause life? Life is like this fundamental thing to physics. It's definitely something to explain, if that was the case. Back to the book. If the laws of physics are fine-tuned, as they seem to be, then there are two possibilities. Either those laws are the only ones to be instantiated in reality as universes, or there are other regions of reality, parallel universes, and here he's not talking about the quantum parallel universes, he's talking about universes with physical laws. So let me just repeat that, back to the book. If the laws of physics are fine-tuned, as they seem to be, then there are two possibilities. Either those laws are the only ones instantiated in reality as universes, or there are other regions of reality, parallel universes, with different laws. In the former case, we must expect there to be an explanation of why the laws are as they are. It would either refer to the existence of life or not. If it did, that would take us back to Paleys Problem. It would mean that the laws had the appearance of design for creating life, but had not evolved. Or the explanation would not refer to the existence of life, in which case it would leave unexplained why, if the laws are as they are, for non-life related reasons, they are fine-tuned to create life. If there are many parallel universes, each with its own set of laws of physics, most of which do not permit life, then the idea would be that the observed fine-tuning is only a matter of parochial perspective. It is only in the universes that contain astrophysicists that anyone ever wonders why the constants seem fine-tuned. This type of explanation is known as anthropic reasoning. It is said to follow from a principle known as the weak anthropic principle. Though really no principle is required, it is just logic. The qualifier weak is there because several other anthropic principles have been proposed, which are more than just logic, but they need not concern us here. Just as a side note, the link to my paper below contains a little bit of a summary of some of the other anthropic principles. Back to the book. However, on closer examination, anthropic arguments never quite finish the explanatory job. To see why, consider an argument due to the physicist Dennis Sciama, who is, just by the way, this is me talking again, who was one of David Deutsch's supervisors or bosses at some point. Back to the book. Imagine that at some time in the future, theoreticians have calculated for one of those constants of physics the range of its values for which there would be a reasonable probability that astrophysicists of a suitable kind would emerge. Say that range is from 137 to 138. No doubt the real values will not be whole numbers, but let us keep it simple. They also calculate that the highest probability of astrophysicists occurs at the midpoint of the range, when the constant is 137.5. Next, experimentalists set out to measure the value of that constant directly, in laboratories or by astronomical observation, say. What should they predict? Curiously enough, one immediate prediction from the anthropic explanation is that the value will not be exactly 137.5. For suppose it were. By analogy, imagine that the bullseye of a dartboard represents the values that can produce astrophysicists. It would be a mistake to predict that a typical dart that strikes the bullseye will strike it at the exact centre. Likewise, in the overwhelming majority of universes in which the measurement could take place, because they contain astrophysicists, the constant would not take the exactly optimal value for producing astrophysicists, nor be extremely close to it compared with the size of the bullseye. So, Sciama concludes, if we did measure one of those constants of physics and found that it was extremely close to the optimum value for producing astrophysicists, that would statistically refute, not corroborate, the anthropic explanation for its value. Of course, that value might still be a coincidence, but if we were willing to accept astronomically unlikely coincidences as explanations, we should not be puzzled by the fine-tuning in the first place, and we should tell Paley that the watch on the heath might just have been formed by chance. Furthermore, astrophysicists should be relatively unlikely in universes whose conditions are so hostile that they barely permit astrophysicists at all. So if we imagine all the values consistent with the emergence of astrophysicists arrayed on a line, then the anthropic explanation leads us to expect the measured value to fall at some typical point, not too close to the middle or to either end. However, and here we are reaching Sciama's main conclusion, that prediction changes radically if there are several constants to explain. For although any one constant is unlikely to be near the edge of its range, the more constants there are, the more likely it is that at least one of them will be. This can be illustrated pictorially as follows, with our bullseye replaced by a line segment, a square, a cube, and we can imagine this sequence continuing for as many dimensions as there are fine-tuned constants in nature. Arbitrarily define near the edge as meaning within 10% of the whole range from it. Then in the case of one constant, as shown in the diagram, 20% of its possible values are near one of the two edges of the range, and 80% are away from the edge. But with two constants, a pair of values has to satisfy two constraints in order to be away from the edge. Only 64% of them do so, hence 36% are near the edge. With three constants, nearly half the possible choices are near the edge. With 100 constants, over 99.999999% of them are. So I'll just pause there for a moment. So the way that you can do the maths for the square here is to say, well, you've got 0.8 in the horizontal direction and 0.8 in the vertical direction, and 0.8 times 0.8 is 0.64, leaving 1 minus 0.64, which is 0.36 near the edge. And then if you've got the cube, you've got 0.8 times 0.8 times 0.8. And if you do 1 minus 0.8 times 0.8 times 0.8, then you have 0.488 or 48.8%. Back to the book. So the more constants are involved, the closer to having no astrophysicists a typical universe with astrophysicists is. It is not known how many constants are involved, but it seems to be several, in which case the overwhelming majority of universes in the anthropically selected region would be close to its edge. Hence, Sciama concluded, the anthropic explanation predicts that the universe is only just capable of producing astrophysicists, almost the opposite prediction from the one that it makes in the case of one constant. On the face of it, this might in turn seem to explain another great unsolved scientific mystery known as Fermi's problem, named after the physicist Enrico Fermi, who is said to have asked, where are they? Where are the extraterrestrial civilizations? Given the principle of mediocrity, or even just what we know of the galaxy and the universe, there is no reason to believe that the phenomenon of astrophysicists is unique to our planet. Similar conditions presumably exist in many other solar systems. So why would some of them not produce similar outcomes? Moreover, given the timescales on which stars and galaxies develop, it is overwhelmingly unlikely that any given extraterrestrial civilization is currently at a similar state of technological development to ours. It is likely to be millions of years younger, i.e. non-existent, or older. The older civilizations have had plenty of time to explore the galaxy, or at least to send robot space probes or signals. Fermi's problem is that we do not see any such civilizations, probes, or signals. Many candidate explanations have been proposed, and none of them, so far, are very good. The anthropic explanation of fine-tuning, in the light of Sciama's argument, might seem to solve the problem neatly. If the constants of physics in our universe are only just capable of producing astrophysicists, then it is not surprising that this event has happened only once, since its happening twice independently in the same universe would be vanishingly small. Unfortunately, that turns out to be a bad explanation too, because focusing on fundamental constants is parochial. There is no relevant difference between 1, the same laws of physics with different constants, and 2, different laws of physics. And there are infinitely many logically possible laws of physics.
If they were all instantiated in real universes, as has been suggested by some cosmologists such as Max Tegmark, it would be statistically certain that our universe is exactly on the edge of the astrophysicist producing class of universes. So this is great. Often, this is me talking, my commentary, often in these discussions about fine-tuning, there's a fixation on the constants, purely upon the constants, and less attention is paid to the form of the laws of physics themselves. And the form of the laws of physics is a crucial thing that we could manipulate if we were some all-powerful God or if we had control of various different universes. And so David's about to get to the discussion about why, assuming that there are an infinite class of universes out there, all of which instantiate completely different physical laws, really doesn't solve the problem whatsoever. The problem is definitely there. So we will proceed. He writes, "We know that that cannot be so from an argument due to Feynman, which he applied to a slightly different problem. Consider the class of all possible universes that contain astrophysicists, and consider what else most of them contain. In particular, consider a sphere just large enough to contain your own brain. If you are interested in explaining fine-tuning, your brain, in its current state, counts as an astrophysicist for these purposes. In the class of all universes that contain astrophysicists, there are many that contain a sphere whose interior is perfectly identical to the interior of your sphere, including every detail of your brain. But in the vast majority of those universes, there is chaos outside the sphere, almost a random state, since most random states are by far the most numerous. A typical such state is not only amorphous, but hot. So in most such universes, the very next thing that is going to happen is that that chaotic radiation emanating from outside the sphere will kill you instantly. At any given instant, the theory that we are going to be killed in a picosecond, hence, is refuted by an observation a picosecond later, whereupon another such theory presents itself. So it is a very bad explanation, an extreme version of the gambler's hunches. The same holds for purely anthropic explanations of all other fine-tunings involving more than a handful of constants. Such explanations predict that it is overwhelmingly likely that we are in a universe in which astrophysicists are only just possible and will cease to exist in an instant. So they are bad explanations. This is this idea of Boltzmann brains, where if you assume randomness obtains out there in the universe or out there in reality beyond our universe, then randomness implies that everything that can possibly happen is going to happen somewhere or other at some point. And when we say possible to happen, logically possible could happen. And that includes you, yourself, your brain, your consciousness right now popping into existence and then popping out of existence now. And what we're saying about that here, what David's saying about that here is that that's an exceedingly bad explanation. It doesn't explain anything. It doesn't explain why the laws of physics have the form that they do. Of course, everything could pop into existence now and then pop out of existence. I think I first heard this at university, that God could have done that he could have clicked his fingers and everything comes into being, including you with your memories right now, and at any moment it could disappear again as well. And I found that an exceedingly bad explanation at that time as well. Back to the book. On the other hand, if the laws of physics exist in only one form, with only the values of a few constants differing from one universe to another, then the very fact that laws with different forms are not instantiated is a piece of fine-tuning that anthropic explanation leaves unexplained. The theory that all logically possible laws of physics are instantiated as universes has a further severe problem as an explanation. As I shall explain in Chapter 8, when considering infinite sets, such as these, there is often no objective way to count or measure how many of them have one attribute rather than another. On the other hand, in the class of all logically possible entities, those that can understand themselves as the physical reality that we are in does, are surely, in any reasonable sense, a tiny minority. I'll just pause there for a moment. So when he says that there's this class of all logically possible entities, there is a tiny sliver of logically possible entities that can understand themselves, namely universes like ours in which we have evolved and we now are part of the universe that is understanding itself. Just continuing. So that's a tiny minority, he says. The idea that one of them just happened without explanation is surely just a spontaneous generation theory. In addition, almost all the universes described by those logically possible laws of physics are radically different from ours. So different that they do not properly fit into the argument. For instance, infinitely many of them contain nothing other than one bison in various poses and last for exactly 42 seconds. Infinitely many others contain a bison and an astrophysicist. But what is an astrophysicist in a universe that contains no stars, no scientific instruments, and almost no evidence? What is a scientist or any sort of thinking person in a universe in which only bad explanations are true? Almost all logically possible universes that contain astrophysicists are governed by laws of physics that are bad explanations. So should we predict that our universe too is inexplicable or has some high but unknowable probability to be? Thus, again, anthropic arguments based on all possible laws are ruled out for being bad explanations. For these reasons, I conclude that, while anthropic reasoning may well be part of the explanation for apparent fine-tuning and other observations, it can never be the whole explanation for why we observe something that would otherwise look too purposeful to be explicable as coincidence. Specific explanation in terms of specific laws of nature is needed. And here we've finished the subsection of the fine-tuning part, and we go into the conclusion about the whole chapter. So some remarks are made about neo-Darwinism as well. And he writes, "The reader may have noticed that all the bad explanations that I have discussed in this chapter are ultimately connected with each other. Expect too much from anthropic reasoning, or wonder too carefully about how Lamarckism could work, and you get to spontaneous generation. Take spontaneous generation too seriously, and you get to creationism, and so on. That is because they all address the same underlying problem, and are all easily variable. They are easily interchangeable with each other, or with variants of themselves, and they are too easy as explanations. They could equally well explain anything, but neo-Darwinism was not easy to come by, and it is not easy to tweak. Try to tweak it, even as far as Darwin's own misconceptions, and you will get an explanation that doesn't work nearly as well. Try to account for something non-Darwinian with it, such as a new, complex adaptation of which there were no precursors in the organism's parents, and you will not be able to think of a variant with that feature. Anthropic explanations are attempting to account for purposeful structure, such as the fine-tuned constants, in terms of a single act of selection. That is unlike evolution, and it cannot work. The solution of the fine-tuning puzzle is going to be in terms of an explanation that will specifically explain what we observe. It will be, as Wheeler put it, an idea so simple that we will all say to each other, how could it have been otherwise? In other words, the problem has been not that the world is so complex that we cannot understand why it looks the way it does, but it is that it is so simple that we cannot yet understand it. But this will be noticeable only with hindsight. All those bad explanations of the biosphere either fail to address the problem of how the knowledge and adaptations is created, or they explain it badly. That is to say, they all underrate creation. And, ironically, the theory that underrates creation most of all is creationism. Consider this. If a supernatural creator were to have created the universe at the moment when Einstein or Darwin or any great scientist appeared to have just completed their major discovery, then the true creator of that discovery, and of all earlier discoveries, would have been not that scientist, but the supernatural being. So such a theory would deny the existence of the only creation that really did take place in the genesis of that scientist's discoveries. And it really is creation. Before a discovery is made, no predictive process could reveal the content or the consequences of that discovery. For if it could, it would be that discovery. So scientific discovery is profoundly unpredictable, despite the fact it is determined by the laws of physics. I'm just going to pause there because that's amazing, and this brings in some issues that people have about free will, and we're starting to think that free will is tied up very much with this idea of creativity, or it at least is synonymous in a way with creativity. That it doesn't matter what the laws of physics are, the laws of physics we cannot derive from the laws of physics the discoveries in science themselves. As he says there, that it's not possible for a predictive theory, a predictive process to reveal the content of discoveries, of scientific discoveries. Because if there was such a theory that could predict the content of scientific discoveries, then it would include that discovery, it would be that discovery. So scientific discovery is profoundly unpredictable, the growth of knowledge is profoundly unpredictable, even though it is determined by the laws of physics. And this is a subtle and often misunderstood point. Back to the book. I shall say more about this curious fact in the next chapter. In short, it is due to the existence of emergent levels of explanation. In this case, the upshot is that what science and creative thought in general achieves is unpredictable creation, ex nihilo. So does biological evolution. No other process does. Creationism, therefore, is misleadingly named. It is not a theory explaining knowledge as being due to creation, but the opposite. It is denying that creation happened in reality by placing the origin of the knowledge in an explanationless realm. Creationism is really creation denial, and so are all those other false explanations. The puzzle of understanding what living things are and how they came about has given rise to a strange history of misconceptions, near misses, and ironies. The last of the ironies is that the neo-Darwinian theory, like the Popperian theory of knowledge, really does describe creation, while their rivals, beginning with creationism, never could. That's the end of the chapter. That's wonderful. So if I could just recap that bit there. Creationism says that God created everything, which means that God created all of the knowledge, including the knowledge of how Einstein got to his theory of relativity, including how Darwin got to his theory of evolution by natural selection. So everything that people create isn't actually a creation because it was already there in the mind of God at some point. And so creationism is denying actual creativity. Actual creativity is done by people and it's inherently unpredictable. And so this is the weird thing about creationism. It denies actual creativity. What explains actual creativity? Two things. The theory of evolution by natural selection, neo-Darwinism, and Popperian epistemology, the way in which knowledge grows. We understand neither theory perfectly well. Neither theory are we able to turn into a predictive theory such that we can program, we can't capture the algorithm for either of these theories into a computer program. But we understand something. There's a whole bunch of people who deny neo-Darwinism, creationists and so on. There's a whole bunch of people who deny Popperian epistemology as well, or who fail to understand either. Often I think that's actually the case. The creationists just don't understand neo-Darwinism, and people who deny Popperian epistemology just aren't familiar with it enough. Anyway, this was one of the most exciting parts of the book for me so far, this idea of fine-tuning. Whole bunch of links down below to books related to this. I'll try and make a video of my own paper as well. Thanks for watching, and we'll see you in Chapter 5, the reality of abstractions next, which is also very exciting. This has a lot to do with the nature of mathematics, which is in the Fabric of Reality. It was one of my favourite chapters of the Fabric of Reality, and so I might do a little bit of meshing of those two together. It's a very exciting chapter. It's a very poorly understood chapter as well. So reality of abstractions is up next. See you next time.